Hi. So today I'm just going to give a broad description of what's been happening in ESMF regridding since the last time we met. So first, I'm just going to give a super brief overview of ESMF regridding in general, just in case there's anyone in the audience who doesn't know about it. And then I'm going to give some updates on some new work we've been doing. In particular, I'm going to talk about our work bringing in extrapolation methods, some new optimization capabilities that are useful for regridding, some other new regridding features, our work bringing MOAB in to replace some low-level mesh representation capabilities in ESMF, bit-for-bit testing, and upcoming features in the next release. So ESMF regridding is a high-level interpolation weight, parallel interpolation weight generation system that scales to many thousands of processors. We support a wide range of grids, from logically rectangular tiles to unstructured meshes, 2D or 3D grids, spherical or Cartesian coordinates. We support a range of interpolation methods and various options for you can apply while you're calculating regridding weights. This is all available through our Fortran API, a Python API. We actually have a C API, even though it's not on the slide, and there's some standalone tools. So first I'm going to talk about extrapolation. When you do regridding, often you have destination points that can't be remapped, either because there's a mismatch in the source and destination masks, or some of the destination points lie outside the source grid. Before, users would have to spend time implementing a solution to this, figuring out how to fill those points. So what we've done is we've added a new option to ESMF regridding, where you can just set one parameter in the regridding, and it goes through and generates weights for those missing destination points. And those extrapolation weights are incorporated into the regridding weights. And so all you have to do is set one parameter in the regridding, and voila, the missing destination points are filled. And the nice thing about having them incorporated in the regridding weights is it's easy to experiment with. You can just turn it on and your regridding flow should work as usual. So we support 4 types of regridding, and you can see it, 4 types of extrapolation, and you can see them described at the bottom of the page there. But what I'm going to do is I'm going to talk about them on the next page, where I have some pictures of them. So if you look at the top left-hand side, that shows the original source grid and field. On the top right-hand column, you can see what would happen if you did bilinear interpolation from that source grid and field to the destination that I'm using as an example. The black region is just a masked area in the destination grid that I added to illustrate some properties of the extrapolation. So if you look at the square below that, that shows our nearest neighbor extrapolation method. And what that does is it just grabs, to fill each of those destination points, it just grabs the value in the nearest source point. And so it just, the data just sort of flows outward from the interpolated, the part that was regridded upward. But as you can see, it jumps over the masked regions and just grabs points on the other side. The other thing to notice is it's a little bit blocky, because as it's just grabbing the whole value from the destination point. So as it switches from one closest point to the next, there's a jump in the values. So below that, you can see another extrapolation method we've implemented. And what this is inverse distance weighted averaging. So the user specifies a number of points, and for each unmapped destination points, it finds that number of closest points and blends the values together, and that gives you a smoother result. In the next column, in the right-hand side in the middle, you can see another type of extrapolation we added. So this is creep fill, and what this does is, for your destination, it takes your destination the regridded destination values and moves them outward one level at a time, going around masked regions in the destination. And so if you look at the picture, you can see how the green next to the red sort of flows up around the masked region and across the top instead of the red being jumped across that masked region. And so this is useful in cases like not long narrow islands where you don't want to, if you're extrapolating to the other side, you don't want to grab the values on the other side of the island. What you want them to do is sort of follow the, you know, sort of maybe the flow of the ocean would go around the island to the other side. So the problem with this though is because it avoids, because it doesn't cross masked regions, if you have a hole in your mask, if you have a region in your mask that's completely region in your grid that's completely surrounded by mask, the creep won't get in there. So we added another method that you could see at the bottom that does the creep fill first and then does last step of nearest neighbor regridding to fill in those missing points. Okay, so now I'm going to switch to some other optimization capabilities we added. So the first of these is the ability to read and write a route handle. So a route handle is ESMF's method of encapsulating a sparse matrix multiply. So what we do is we pre-compute all the things you need to do a sparse matrix multiply, the communication pattern, the buffer sizes, etc., to make applying the sparse matrix multiply as fast as possible. So this doesn't take a lot of time, but it does take some time. Usually it's not a big deal because it happens during initialization, which happens once, and you're usually applying the route handle over and over. But if you want to optimize your initialization as fast as possible, you can use this method to write out your route handle, and then the next time you run, you can read it in, and it's faster even than pre-computing the regridding weights. So the next thing I want to talk about are VM epochs. And so this is an optimization capability that what you can do is you can use two VM epoch calls and bracket a set of sparse matrix multiply calls like regrids or redists. It can be any mix of those. And what it does is it tells ESMF to take all the communication in there and accumulate it and then send it in one chunk. And this is what this lets you do is trade off more memory for a faster time in cases where that's appropriate. And so now I'm going to just show you a little graph about that. So this is a case that a user came to us where they had a forecast component running on 400 processors, writing to a, or communicating with the write component running on 27 processors. And it was going slower than they wanted it to. And so across the bottom of the graph, horizontally, that's different forecast pets, and across the side vertically is the send times. And the thick lines at the top show basically that was the time it was taking before we did an optimization. And what was happening is because it was doing a whole bunch of sends between a lot of processors and a fewer processors. Those sends were waiting. It was non-blocking communication, but the sends had to wait till the buffer emptied and then go to the next one, you know, as it was going through. And so by doing the VM epochs and accumulating all all that communication and doing it in one chunk, we were able to reduce the time and to do the sends by 85%, which made the users happy and they could move on. So with their project. So another new capabilities, another set of capabilities that we brought in are dynamic masking is one of them. So we've had static masking for a while, where you can tell the regrid code to not use a certain portion of the source mesh, or in the regridding, or don't regrid to some part of the destination mesh. And so, but often you can have things like an ICE component where bad values are changing in the source grid, or you don't want to write to some changing set of things in the destination grid. And so what the dynamic masking lets you do is you can set a couple of trigger values, a source and a destination trigger value, and a function in the regrid weight application. And if one of those trigger values shows up in the source field or in the destination field, then the regridding calls you this function, a user-defined function, and that will let you change the output of the output to the destination of the regridding. And so, say you have this bad value in the mask side, the source side, then what you could do is, you know, see it and then write out indication of a bad value to the destination side. Another new capability we've added is a destination status field. And what this is that you can take an integer field, the same size as the destination field, and pass it into the regridding. And the regridding will go through, and when the weights are calculated, will go through and fill that destination field with flags. For each point of the destination, it'll tell you what happened to it during the regridding, whether it was successfully masked, whether it wasn't masked because there was a source mask or a destination mask, or it was extrapolated to. So this is really useful in debugging, and it also lets you modify the source grid, the destination grid, if you want to, based on the regridding behavior. Like if you have a source point that didn't get mapped to because it was outside the source grid, you could do something different there. And I think I'm going to skip that last point just because I'm running behind. But let me know if you have any questions about it later. Okay, so now I'm going to talk a little bit about our incorporation of MOAB into ESMF underneath the to replace the part of our regrid code. And so ESMF regridding and mesh are built on a custom 3D finite element code. The idea here is to replace that underneath custom finite code with the externally developed MOAB library. And the idea here is to gain sort of the community benefits of using an externally developed code like the users of ESMF get, right? So as things are improved in MOAB for other users, we get the benefits of that. And also we're expecting to get some new capabilities from MOAB, some things we don't have implemented in our code, and some performance benefits in some cases. So how is this, incorporation of MOAB going? So right now you can turn on a flag and build an ESMF mesh optionally on MOAB underneath. And using that, you can do a lot of the ESMF regridding type things with that MOAB code, with the ESMF code using MOAB underneath to represent the mesh. But there are still a few things we need to finish, and then we've been testing along, but we're also going to do lots more testing once things are finished. So from the user perspective, this change should be transparent. The user shouldn't have to do any kind of code changes because of this, because it's happening way down low in ESMF. MOAB builds automatically as part of ESMF right now, and so the user shouldn't have to add another dependency. And we're going to give the user lots of time to make this change. We're going to spread it out over a few releases. I'm sorry, not to make the change, but to make sure the change isn't causing any problems for them. So we're going to bring it in one release, and we're just going to go slowly over a few releases to give users a chance to try it, to make sure that they're not having problems with the new version. So next slide.
Now it's 2 more minutes.
2 more minutes, thank you.
Yeah.
Okay, so the last thing I'm going to talk about is our new bit-for-bit testing. So answer changes are a big deal for operational models. So what we want to do is to let them know ahead of time if changes have occurred in ESMF and why. So our new bit-for-bit testing watches for any changes in our nightly offline regridding tests. And if there's any bitwise change in any small change in any of the regridding weights, it lets us know, and then we investigate it and figure out why that happened, and we record it in a document. And then also, it's not just testing. As we're doing development, if we think we're going to change if we do something that we think are going to change answers, we also record it. And so the output from all this is a list of expected bit-for-bit changes between each ESMF tag. And so what this lets us do is, as we're handing out snapshots, we can tell users if they can expect changes between the last snapshot they were using. And also, starting with the last release as some of the output during our release process will be a list of expected bit-for-bit changes since the last release. Okay, and so beyond the stuff I've talked about, some other things we expect to come out in the next release are I talked about creep fill, and right now what you do is you specify a number of levels to creep outward. The problem is it's sometimes not obvious how many you want to creep outward. So what we want to do is add a version of this where you can just say creep as far as you can, and the creep fill will just crawl through the mesh and do reachability to find any unmapped points that it can. Another thing we want to add is a way for users to turn on more expensive testing in the regridding. Right now, we do whatever checks we can in the regridding that aren't extremely time expensive. But what we want to do is we want to have a way for the user to turn on a flag so that we can do some of these more expensive checks, like to see if the grid overlaps itself, or check for consistency across coordinates across all the processors. Take support requests and fix things, help you fix things if you need us to. And then we're going to, like I mentioned before, we're going to bring in MOAB, at least an initial version of it. These are just some references for the different regridding methods. Thank you. Let me know if you have any questions.